The fastest growing AI startups in 2025 that was making around $125 million in ARR were averaging 25% gross revenue and sometimes even negative. And a big reason for that is inference cost alone was eating 23% of the entire revenue. This was happening because every inference call, be it deeply architectural analysis or even explaining a six-line function, was hitting the same frontier model at the same price. In this video, you will learn how to fix that. To understand the problem, let's take an example of a coding agent. In a single session, it does 5 different types of tasks, such as explaining a code base, looking for documentation, writing new function, searching for bugs, explaining different methods. These tasks have different cognitive ability. A frontier model like Claude Opus 4.1 at $15 per million input tokens and $75 per million output tokens is great for something like deep analysis, but for tasks like explaining an 8-line function or doc lookup, it's an overkill. Inference routing is the technique where each LLM call is routed to the cheapest possible models that is capable of handling it at your required quality level, frontier for tasks that need it, and cheaper open source models for tasks that don't. Before you implement routing, you need to know answer to two main questions. What does your call distribution look like? And what quality floor can you accept for tasks that you are routing to cheaper models? Only when you know both of these, that is when the cost math actually works. And here's how you can figure it out. To measure your distribution, add a logging wrapper around every LLM call in your agent. Log the token count, whether the prompt contains a code block or file path, whether it's a generative request, write, build, create, or a retrieval request, explain, find, summarize, and the turn depth in the conversation. Once you have a few thousand calls logged, you can label them by task type and see the shape of your traffic. Depending on your workload, your coding agent's calls breakdown can look something like this. Numbers will be different. Instrument before you route. The shape, though, is consistent with what research supports. Microsoft Research's Hybrid LLM paper says that in real world, query difficulty is heavily skewed. Most queries are classified as easy and there is no measurable quality drop with smaller models. Cursor's own job posting for the model routing and infrastructure team describes dynamically choosing the best model to route each request based on cost, quality, and latency as the most infrastructurally challenging problem that they are facing while scaling millions of requests per day. The second question on what quality floor can you accept depends on your task categories and needs you to run an actual eval. There are two options. You can either run evals on DigitalOcean or you could also use a DIY methodology that I'll just show in the next few seconds. I ran 50 prompts, 25 method explanation, 25 doc search through both Claude Opus and Llama 3.1 70 billion on DigitalOcean serverless inference, using Claude Opus as an LLM judge, scoring each response on correctness, completeness, and code accuracy on a 1 to 5 scale. On doc search, the open source model scores 2.05 versus 3.33 for Frontier. At a 60% Frontier win rate, the smaller model still produces acceptable output on 4 in 10 queries. And for a task that's 25% of your traffic and requires no reasoning, that's a defensible routing target if you're willing to accept occasional shallow answers on refresh lookups. For method explanation, Frontier scores 4.84 versus 4 for open source, with an 84% Frontier win rate. Whether it matters depends on your product. A 4.0 explanation of an 8-line utility function may be good enough for your users, even if it's not as thorough as a 4.84, only you can make that call for your use case. The methodology I just showed works well, but there is a limitation. It doesn't scale. Every time you change your routing policy or add a model to the pool, you need to rerun it. DigitalOcean's model evaluations, which is now in public preview, is built for exactly this. Upload your own production representative dataset, select your candidates, a single model, a router configuration, or bring your own model on dedicated inference, and run them against the same judge with the same metrics in just one job. You get correctness, latency, and cost per token across all candidates on the same rows. Now let's go back to the maths to understand what it means in dollars. With 10,000 sessions in a month and an average of 5 LLM calls per session, you are making 50,000 inferenced calls. All Frontier cost adds up to a weighted average of 1,443 input tokens,
433 output tokens per call. The input cost is around 50,000 multiplied by 1443 per 1 million token multiplied by $15, which sums up to $1082, and the output cost is 50,000 multiplied by 433 per 1 million token multiplied by $75, which comes around $1,624, and the monthly total is around $2,706. If you are charging 50 cents per session, that's $5,000 revenue against $2,706 inference cost. Gross margin on inference is around 46%. Now route 77% of that traffic, the simpler task, to an open source model at $0.2 per million tokens, both in and out, for which you can use something like DigitalOcean serverless inference with Llama class models. Now the model cost looks like this. Frontier calls, which is around 23%, comes around $622. Open source calls, which is around 77%, comes around $14. Now the new total is $636 per month compared to $2,706 that we calculated before.
With the same revenue, your gross margin now jumps to around 87%. This approach has been used by companies such as Lovo that reported around 40% cost reduction by using Inference Router by DigitalOcean while maintaining speed, accuracy, and reliability. When teams decide to reduce inference cost, the first instinct is to build a routing layer, a cheap classifier which decides which model takes up which task.
It looks like this. Claude Haiku is $1 per million input and $5 per million output. For 50,000 routing calls at around 200 input and 20 output tokens each, the overhead is around $15 per month. That looks cheap, but this is the double taxation problem. You are paying for every call twice, once for the router, once for the actual model. Along with the cost, you're also hurting latency. Every single inference call now has a router call in front of it. Even a fast high-Q call adds around 300 to 600 milliseconds. That's visible to users on every request. There's a subtler problem with this classifier that doesn't show up until you're in production. That prompt 200 truncation is doing real work and not in a good way. The classifier is making a simple versus complex decision on the first 200 characters of a prompt that might be 1400 tokens long. It's not reading the code block, not seeing the stack trace, and not picking up the cross-file references that make something genuinely complex. It's pattern matching on the opening sentence. What actually predicts routing complexity isn't semantic content, it's structural signals, prompt length, presence of code blocks or file paths, whether the request contains a comparative operator, whether it's generative versus retrieval. A classifier trained specifically on those features, not doing zero-shot semantic inference on truncated text, is structurally more accurate and an order of magnitude faster because it doesn't need to run a full forward pass on your prompt. This knife fix reduces the cost, but it adds latency, a new failure method, and also adds a lot of maintenance work.
A purpose-built router solves this differently. Rather than running a forward pass on your truncated prompt, it classifies on structural features such as token count, code markers, and verb patterns. Two paths from here, either you build it yourself or use a managed layer. I'll show DigitalOcean's Inference Router as an option with no additional cost on top of inference spend, and you can also evaluate it against your own constraints.
Because the inference router isn't passing a forward pass on your prompt, it's evaluating a feature vector of token count, code markers, and turn depth. The overhead is a fraction of what Haiku classifier adds. The exact amount depends on your load and network conditions, but the architecture reason it's faster is that there is no model inference happening at routing time. The inference router pulls up live cost, latency data, and re-ranks your model pool in real time. If a model is degraded, it automatically shifts to the next best fit. The routing layer is built with no additional cost, and this alone fixes the double taxation problem in inference. Let's see how you can build it with DigitalOcean's Inference Router. In the DigitalOcean control panel, under Inference, you land on the Create a Router page. Give it a name. We are calling ours Coding Agent Router, and a description. That description is used as a routing prompt, so be specific. Something like routes requests from a coding agent across tasks ranging from architectural analysis to a simple documentation lookups. Next, we need to define our tasks. We are creating three. First is deep analysis. The description goes something like deep code-based analysis, multi-file architecture refactoring, complex algorithm design requiring full context. The model we are using is Claude Opus 4.6. and the policy chosen is fastest. This is the task that earns its cost. Next, what we are doing is adding a second custom task. We name it code generation, and the description is something like writing new functions, multi-step debugging, code review. Claude Sonnet 4 is selected, and the policy is cheapest. This doesn't need opus level reasoning, it needs readability, which is why we are using the model that we just mentioned. The third task is lightweight tasks, and the description that we are using is function explanation, docstring generation, simple bug identification, and documentation search. Here we are routing to Llama 3.3 Instruct 70 billion open source model, and it has the cheapest policy. This is the 57% of your traffic that doesn't need a frontier model. 3 tasks covering the full call distribution, and now the fallback models handles anything the router can't classify. We are setting Claude Opus, HiQ, and Sonnet as the fallback chain in priority order. Hit create router, and the entire integration in your existing code is one string change. Replace the model name with router, coding agent router, and that's it. Before you implement this, here's where it breaks. First, cold routing. When a request type appears that the router hasn't seen at volume in your traffic, it defaults to frontier. That's the right default, but if you ship a new feature that generates a previously unseen prompt structure, expect 100% of that new traffic to hit the frontier until the router has enough signal to classify it. Second, long context requests. Routing a 100K token code-based analysis to an open source model to save $0.02 is false economy. Make sure your routing policy has a context length ceiling above a certain token count. Always route to frontier regardless of task type. Third, simple versus complex will get you to maybe 80% routing accuracy. The last 20% requires a multi-class routing model that distinguishes between task types, not just complexity levels. If you are seeing misclassification on function generation versus bug fixing tasks that look structurally similar but have very different quality requirements, that's where a multi-class approach pays off.
What we can conclude from this is that for lightweight tasks, you use lightweight models, and for reasoning heavy tasks, you use the frontier models. But the main question is if you should build it yourself or if you should use a solution that has already solved it. Building it yourself means that you have to maintain an entire system where you're writing the classifier, retaining it as your traffic distribution evolves, and also monitoring for misclassifications. If I were you, I would use a solution that has already solved it. Inference Router is now in public preview. To learn more, make sure that you read the docs that's linked in the description below. If you want to see this extended to a multi-agent system where different agents in the same system have different routers tuned to their workload, drop a comment. And with that, I'll see you in the next one.